This time, I think I'll do a mailbag video for a change, but I'll still make it educational for those who like my tutorial videos. This is an Aneng An8008 digital multimeter ordered from Banggood for $14.99 plus 62 cents shipping. It was a seasonal deal. The regular price appears to be around $24. This meter was a present from a family member, so I wasn't the one who opened it. Too bad, because I could have used this dagger to open the packaging. In terms of equipment, I can't compete with the YouTubers with $1,000 oscilloscopes and every gadget imaginable, so I'll try to be different by showing and using unusual things, thus the dagger, instead of the usual utility knife. But apparently these scissors would have been more appropriate for the packaging this meter came in. Since the family member isn't a technical person, so to speak, I had to research which meter to get. I used to wonder why there were so many multimeter review videos on YouTube, but this research showed why. It's hard to know what to buy. Sure, if money was no object, get the most expensive multimeter, or just go with a fluke. But if you're trying to get an inexpensive one, it's hard. I had known that Paul from the Learn Electronics YouTube channel recommends this meter, but since I was looking for a $10 meter, this one seemed beyond consideration. I want to thank Paul for personally pushing me to pick this meter. By the way, even Dave Jones from EEV blog likes this meter, as much as he can like an under $25 meter. This meter uses two AAA batteries, which are not included. I would rather it have been AA, since I have more rechargeable AA's. Also, the meter does have the problem with the stand that every reviewer mentions. It isn't very sturdy. The meter also comes with some nice accessories. You get an extra set of cables with changeable parts on each end. I don't know how good the metal is on these parts. I imagine it could be easy to strip the threads. So I recommend deciding what you want most and keeping the cables that way. Most, if not all, experts say to throw away the cables that come with any cheap meter and buy a professional set. But that's not always possible for people on a budget, so I'll use these in this video. By the way, there is one set of ends I wish was included. Test hooks. That's why I wired this up. You would use an alligator clip on the wire, or it could also connect a banana plug with a longer cable to the test hook. The meter also comes with some instructions. You probably won't be able to read them in this video. Sorry about that. I'm guessing that the number one task most non-technical people use a multimeter for is checking batteries. Continuity probably is high up there as well. With battery testing, however, there is something to keep in mind. Just putting the test leads up to the battery won't give you the whole picture when a meter is in the general voltage setting. This is because the battery isn't being put under a load. The battery could show a high voltage reading, but be weak when being used, since the battery could have developed a high internal resistance. So you really need to put a load across the battery. Some people recommend a 100 ohm resistor, some recommend a 10 or 20 ohm resistor. The lower the resistance, the greater the load. Perhaps it's best to use a value that would best represent what you're using the battery for. I'll use a 20 ohm resistor. It's easier to connect it to the leads like this. This seems to be a rather good battery, since the voltage didn't go down very much. In case it needs to be said, this method won't work well with a car battery. If your meter has battery testing modes, it will use a load resistor already and either measure the voltage or measure the current and calculate the voltage using the known resistance. You wouldn't need to use your own resistor. But this meter doesn't have battery testing modes. By the way, unless you are absolutely sure your live circuit won't ruin your meter in any of the modes, you shouldn't turn the rotary switch while your meter is connected to a live circuit. And remember, even if the power to your circuit is off, there still could be a residual voltage in the various parts such as capacitors. And be extra careful with the current testing modes. I'll be using the backlight a lot in this video, so the readings will show up well. I'm glad this meter has a backlight. I'll also switch to the alligator clip leads. I was pretty cautious while testing current when I first used this meter. I first selected various resistors and used Ohm's law to make sure the current wouldn't exceed the limits of the meter. Even though this power supply is rated at a max of 1 amp from the 5-volt supply, it could still ruin the meter while in the microamp mode. But this wasn't the only precaution I took. I first used my analog multimeter to make sure the current was as I expected from the calculations. Then I used the new meter. Ohm's law states that the voltage is the current multiplied by the resistance. Rearranging the equation means that the current is the voltage divided by the resistance. If algebra is not your thing, here's something I first saw in, I believe, a Heathkit manual. Place your finger over the value you want, and the resulting sections will show how to calculate the desired value. So, in order to use Ohm's law, we need to know the actual resistance of the resistor. It's 5.338 meg. Now we need to know the voltage coming from the power supply. To measure voltage, the meter is placed in parallel with the part being measured. In this case, the power supply, resistor, and meter are all in parallel. It's 4.964 volts. Ohm's law indicates the current should be 0.9299 microamps. Let's see if it is. To measure current, the meter must be in series. I purposely set the meter to a high current setting to show that if you don't know how much current is in the circuit, it's a good idea to start at the high current jack and range. If the value is too small for that setting, it would be safe to go to the lower range. It's also a good idea to get in the habit of returning the red test lead to the voltage testing jack when finished with the meter, so you won't accidentally blow the meter the next time you use it because you didn't realize it was in the amps milliamps current testing jack. In this case, we know the current is low, and that's why in this setting the meter reads 0. Switching to the microamps setting now shows the current is 0.92 microamps. By the way, the microamps range of this meter is something Dave Jones was impressed with. Now for higher current. This resistor measures 20.23 ohms. The voltage is now 4.834 volts. The calculated current is 239 milliamps. The meter shows 246.1 milliamps. In case you think this resistor is big, I've got an even bigger one. Wow, that's bigger than a Rubik's Cube and a tape measure put together. Well, actually, the Rubik's Cube and tape measure are smaller than normal versions that are meant to be keychains. But this resistor is still bigger than the other one. These are big because they are higher wattage resistors. I think this one is 40 watts, and the previous one is 25 watts. According to the color bands, this resistor is 12 meg, which is higher than the maximum 9.999 meg this meter will read, thus the out-of-range result. But there's still a way to test the value of this resistor. Here's an equation for determining the total resistance of two resistors in parallel, or this version if you prefer. What this means is that the resistance of the two resistors in parallel is guaranteed to be less than the least value resistor. So, if I put in parallel a resistor that the meter can read, the total resistance will also be readable. I'll use the 5.338 meg resistor I used before. It now reads 3.748 meg. Rearranging the previous equations gives these equations. Use whichever form you prefer. The value of the unknown resistor is 12.583 meg. It's probably not a perfect method since it's probably compounding measurement inaccuracies, but it's certainly close enough. By the way, remember to consider unit prefixes when doing this calculation. Both these resistors are in the same unit prefix, as a result, all megaohms, so no problem. But if one was kiloohms, for example, care should be taken in doing the calculations. By the way, you can do the same with capacitors. However, since capacitors in series and parallel work the opposite of resistors in series and parallel, you now would use capacitors in series. And the equations are similar. If either capacitor is polarized, observe polarity when connecting everything up. Now for continuity testing. The meter will beep when it detects a closed circuit. If the circuit is closed long enough, the meter will also show the resistance. But this is the usual test, and I'm aiming for the unusual, so I'll use a reed switch that will open and close via a magnetic field. I'll use this magnet. This meter can also measure capacitance. However, to get a true indication of whether a capacitor is still good, you would have to do more tests, like ESR. By the way, you might want to make sure the capacitors are fully discharged before testing them. Be careful while working with any capacitor that might still have a high voltage charge. Here's an electrolytic capacitor. Notice the high pressure safety vents at the top. It's supposed to be 470 microfarads. It measures about 473 microfarads. That's well within tolerances. Here's a capacitor from Sprague, or Sprague. Spray capacitors used to be very common and popular. These were called orange drops. It's supposed to be 0.15 microfarads or 150 nanofarads with a 10% tolerance. It measures 153.7 nanofarads. This is also within spec. This one is supposed to be 0.22 microfarads or 222 nanofarads. It measures 219.4 nanofarads, also within spec. Here's a Nichicon. It's supposed to be 1200 microfarads or 1.2 millifarads. It measures 1.573 millifarads. This is about 30.7% above the rated value. This is most likely okay because since these high-value capacitors are often used for filtering out voltage ripples or smoothing, it doesn't hurt if they are higher than the specified value. The tolerances could be as much as 20% lower and 80% higher. To save time and not be boring, I'll just show these 6 ones at the same time. Pause if you need to. This one is an old one and rather unusual. It's the ceramic shell capacitor from Elmenco. Elmenco used to be a very popular brand. It's supposed to be 0.1 microfarad or 100 nanofarads with a 20% tolerance. It reads 133.8 nanofarads, which is 33.8% above the specified value. That's a bit out of spec, but pretty good for a capacitor that old. Here's 2 capacitors in one. And here's another old capacitor. I won't bother showing its reading because previous tests have shown it's way off. Now for another unusual thing, by today's standards anyway. It's a variable capacitor. It came out of a stereo. This used to be how radio stations were selected in a radio. It ranges from about 0.044 nanofarads to 0.019 nanofarads. Here's a smaller version used in smaller radios. There's a few more capacitors in my 201 electronic kit from Radio Shack that can be measured. I'll test 2 unused capacitors. This one is supposed to be 100 picofarads or 0.1 nanofarads. It reads 0.126 nanofarads. By the way, many people refer to picofarad as puff. This one is supposed to be 0.001 microfarads or 1 nanofarad. It reads 1.07 nanofarads. Rather good. By the way, the currently wired up circuit is experiment number 1 in this kit. It's called the Wheel of Fortune. Maybe if there's enough interest, I'll do a video on this circuit. It's misbehaving a bit because it's pretty picky about the supply voltage. It can't be higher or lower than what it wants. And I'm using rechargeables, so it probably isn't exactly what the circuit wants. Electrolytic capacitors are notorious for going bad. This usually happens if they are not used in a long time. Many owners of old computers will often replace all electrolytics before even turning the computer on, just to ensure it won't blow up, or at least look for bulges in the tops of electrolytic capacitors. Here's an old non-working computer power supply. I'm pretty sure there's a bulge in that capacitor and another one. I don't know if that's the reason the supply went bad, or just the bulge caused by lack of use after it went bad. Now I'll use the diode checker. Here's 3 diodes. The first 2 are somewhat unusual these days. This one conducts in this direction and has a forward bias voltage, also called voltage drop, of 0.56 volts. In the other direction, it doesn't conduct, so it's a good diode. This one reads 0.535 volts, but I know from previous tests that it is bad because it also conducts in the opposite direction with a 2.7 volt reading. But it still might be useful as a temperature sensor. Its resistance, and therefore its voltage drop, changes with temperature. All diodes do, but this one might change more. As the temperature decreases, the voltage drop and the resistance increase. And the third diode has a voltage drop of 0.548 volts. Let's test some LEDs, since they are diodes as well. This red one has a voltage drop of 1.635 volts. Depending on what type of red LED it is, the range is usually around 1.63 to 2.4 volts. This green one reads 1.816 volts. The typical range is around 1.8 to 2.4 volts. This is a different red LED which reads 1.798 volts. This is a yellow LED that reads 1.777 volts. Typical range is also 1.7 to 2.4 volts, and a different green LED which reads 1.825 volts. The meter doesn't fully light the LEDs because it is only providing enough voltage for the LED to turn on. Here's a tip from YouTuber Julian Eilette. In order to easily get the correct voltage and current to light the LED without blowing it, use a 3-volt coin cell battery. I didn't have a good 3-volt one on hand, so I taped two 1.5-volt LR44 type batteries together. Here's a 7-segment display. This one is common anode since all positive LED leads are connected together internally. To light a segment, you just ground the appropriate segment lead. This has a voltage drop of around 1.553 volts. This 7-segment display is a little different than most because it has 2 dots, one on each side. Here's some of the LEDs looking better using the LR44s. This meter also has a frequency counter. I don't have a fancy function generator, so I'll use one that just about everyone has, a computer. I'll use Audacity's waveform generator option to create a square wave for a famous tune. The meter needs about 2 seconds to lock onto the right frequency, so I had to make the duration a little longer than I would have liked. Here's the 5 tones with the selected frequencies versus the measured frequencies. By the way, the resistor between the meter leads and the speaker is there to reduce the effect of the speaker on the reading, and a different octave. Very close results. They might even match exactly without the speaker. I forgot to check the duty cycle, so here's some new footage showing the duty cycle. The generated waveform should have a duty cycle of 50% since it spends the same amount of time high as it does low. And finally, the meter also has a square wave output. I could hear all the tones, but the camera didn't pick up the low tones too well, so I'll use this set of computer speakers to amplify the sound. If it is possible to have fun with a multimeter, you'll definitely have fun with this one. But it would be nice to have a cheap backup multimeter, so you can risk the cheap meter on uncertain circuits instead of a better one. Also good if you are uncertain of what you're doing. I'm not referring to high voltage or high current circuits though. One option is the free multimeters you can get from Harbor Freight. They have coupons all the time. Most are for free with any purchase. If you don't need anything from Harbor Freight, maybe you have a good friend who needs to buy something there and they could use the coupon for you. Or here's one that's $1.99 with no other purchase necessary. These free meters also have a transistor checker, which will tell you the transistor's HFE. If you saw my update video on my Tesla coil, you'll know I probably could have used that feature. For this present, I was willing to go with a $2.84 meter from a local Walmart, but they didn't have any in stock. I'm certainly glad they didn't. By the way, this analog meter does have some advantages. It can take more abuse in terms of incorrect selections or incorrect levels. It's also more fixable since there are less parts, and those parts are easily replaceable. It's not bulletproof though. I didn't damage this meter, but I keep it for spare parts for my other analog meter. The meter seems to have a broken spring or band since the needle won't return to the 0 position. Another advantage of an analog meter is that it shows changes in values better since it doesn't take time to lock onto a value. For those of you who have watched all of this video so far, here's a special bonus. It's an app that can be really useful. It's the ElectroDroid app. It contains all sorts of great electronics information. Resistor color codes, connector pinouts, various calculators, etc. Here you could easily use Ohm's law to determine the desired parameter. This would really come in handy if you're somewhere with no cell phone service or Wi-Fi and you needed to MacGyver something up. And a bonus, if there's no cell phone service and no Wi-Fi, there's no ads. By the way, I'm showing this app on a computer using the Android emulator from the Android SDK since I figured it would show up better than filming a cell phone screen. This app runs even better on the Android x86 OS. Well, hopefully this video has made it easier for you to choose a multimeter, or at least taught you how to properly use one, while also showing some electronics principles and unusual parts along the way. Please subscribe, like, share, comment, etc. And if you click subscribe, click the bell to receive notifications of future videos. Even if you click the bell, still check back from time to time, since YouTube doesn't always notify subscribers.